didn't just say what I just said. So what is a spontaneous process?
It's a reaction. It's a reaction.
There's nothing to do with speed. Good answer. Good answer. How do you determine how fast a reaction is? Activation energy. So all of those things being true. So make sure that you understand in this chapter, if any of the questions ever ask you about the speed of the reaction, you're always going to say, right, you do not have any information. Delta H, delta S, and delta G will never, ever tell you how fast the reaction is going to occur. Just whether it will occur in the direction as it's written or not. Whether it be spontaneous. So College Board is changing the terminology from spontaneous to thermodynamically favorable, and they are still in the process of changing that name. So it may show up as spontaneous or thermodynamically favorable, and you just have to know the book. Your book uses spontaneous. College Board is starting to use thermodynamically favorable, so I'll just say both. They mean the same thing.
I thought you said you can check how fast the reaction will go with the activation energy.
But we're not talking about activation energy here.
Okay.
We are just going to be calculating whether it's endo or exothermic. Does that tell you how much activation energy is required?
No.
No. We'll also be talking about entropy, which I'll get to in a minute. We'll talk about free energy. None of those tell you how fast. They just tell you, will this, once you get the reaction started, will it proceed in this direction or will it proceed in this direction? Spontaneous is ones that proceed in the forward direction.
Oh, is that when it's all the entropy's negative?
Yes.
And it's all positive.
Then it will. Always at all temperatures. Yes. Exactly right. So thermodynamics all compares where are we starting and then where are we going to. So that's why all the calculations or all the variables that we use in thermodynamics are always like delta H and delta G, delta S, like how much is it changing? Not what does it have right now, but how much is it changing? And so all of those that only compare initial and final states are called what kind of functions?
I know. The other one, the state.
State functions. And the other ones are path functions. Kinetic is what is like, what's the pathway that's occurring between, that's path functions. That's what's really important about how much activation energy it's going to take. Like, for example, graphite spontaneously turns into diamonds, which means that that process is what?
Will happen.
That it will happen by itself without any outside intervention once the process gets started. And it is spontaneous or thermodynamically favorable. Do you think it's fast?
No.
It takes like thousands
So it
of
doesn't
hours.
take pressure to make diamonds?
It does. So like given a certain set of conditions with this, like, so there are conditions that you have to know. Pressure is one of them. What do you think is another condition? Temperature. Temperature. Those are two conditions that can determine whether that reaction is going to be spontaneous.
How do you know if this maybe just sort of has a little bit to do with what you just said, but how do you know if the diamond's got to come out perfectly?
That has a lot to do with other things.
Oh, okay.
If there are any other things present, how slowly it forms, but yeah, no.
Yeah.
No. I'm not going to get into that. If you want to study that.
It's just
Yes, we're moving on. All right, so for thermodynamics, there are 3 laws of thermodynamics, and you have to know them all. The first one you already know, you just know it by another name instead of being called the first law of thermodynamics, which it is.
Law of conservation of energy.
That's it, the law of conservation of energy. You've heard it as law of conservation of energy. It's the same thing. The first law of thermodynamics states that the energy of the universe is constant. So as something is releasing energy, something else is taking it in, the amount of energy in the universe is constant. Yes?
Has someone tried finding the constant?
Finding how much that is?
Yeah, it's just a really big number.
I don't know. That's of everything.
What steps do they consider the universe?
For everything in the universe.
Okay, so that's a good question. Like the universe, we could really be talking about the universe, but in chemistry and physics as well, in the lab, what do we call the universe? The system and the surrounding. Yeah? So to be able to understand the second law, you have to know this term, entropy. Entropy is represented by the letter S, obviously. And it is the measure of disorder or randomness, molecular randomness. So whenever you're thinking about entropy, think about as things become more disordered. Don't ever call entropy don't ever say order. like how ordered something is, because it's how disordered, and it will help you with signs. Because what do we say is gonna be always an issue with this chapter? And you will get yourself, some of you are gonna get yourselves mixed up in these signs, but if you always think of entropy as the measure of disorder, so if disorder is increasing, then entropy is positive. If disorder is decreasing, then entropy is negative. But if you say, oh, but it's becoming more ordered, don't say ordered. It's either more disordered or less disordered. Okay, so then the second law of thermodynamics states that the entropy of the universe is always increasing.
Can you just say random or lesser?
Sure. If that helps you. Yeah, you can say random. So, look, we've got this down here was the universe. So the delta S of the universe is always going to be a positive number for any spontaneous process. Meaning, if you're given some stuff on paper and it's like, calculate the delta S of the universe, and you calculate it, and you get a negative number, what does that just mean?
It's messed up.
It's not or it's not spontaneous in that direction. So if it's not spontaneous in the forward direction, then it's going to be spontaneous how? In the reverse direction. Or check and make sure you didn't mess up. But you will calculate things on paper and it will say, is this process thermodynamically favorable? And if you know the delta S of the universe, you can tell me if it's thermodynamically favorable or not. So how do you find the delta S of the universe? What things do you need to know? System and surroundings. So you have to define, how do you find it for the system? How do you find it for the surroundings? How do you calculate that? And the first part of it's a little bit weird, and then we'll get more into how we're going to actually use it. But the first part's going to be kind of a description as to how we define entropy of a system. You guys good with this? Okay, so the entropy of a system is defined as the probability of all of the possible locations of all of the particles in that system. So substances in the gaseous state have more entropy than in the solid state. Why?
There's
More possibilities for the locations of the atoms. Here, they're kind of locked into that shape. They can't really move around. It's kind of just how they're going to be arranged. But here, those particles can move. There's so many probabilities for possible locations that entropy is increasing as you move this way. And actually, there's a decent sized increase as you move from a solid state to a liquid state. But then as you go from liquid to gas, the entropy greatly increases a huge amount. Because some of the questions will be multiple choice. It'll be just like, for which of these is the entropy increasing? Which of these processes? And other ones will be like, which one has the greatest increase in entropy? And you're always looking for the amount of what? Chaos. Disorder, yeah. Embrace the chaos. That's the video. Okay, so how do you figure out how particles are going to be arranged and how can you explain? This is kind of the explain portion when it's like, if you were to put these gas molecules in this container, could they ever possibly all hang out over here?
No.
Yeah, they could. But is that the most likely location that you're going to find them? Are you likely to find them all clumped up together?
No.
Why not? Because if you calculate the probabilities of every single one of the locations and mathematically calculate it, the most likely arrangements are where they're more spread out than all clumped together. And I'll kind of show you in a very, very simplistic picture of it in just a second. So the most likely arrangement is the one that is the most random. And so you could calculate how many different positional probabilities are there for any system given any number of particles. But we're just going to look at for a couple because it starts to get a little bit ridiculous when you're looking at Avogadro's number of particles. I'm not going to draw that many dots on the screen. That'll be fun. Take a while. Okay, so I've copied some stuff. Actually, tried to.
Doesn't this get into superposition?
We won't, but yes. We're not going to get into some of the details.
When something is in a multiple
I
position,
don't
that
think.
one.
Oh.
It's really complicated.
Oh. Are you kidding?
Well, I mean,
Sorry, I don't want this on the video.
It trends you up.
I wasn't trying.
That's just the light electrons being into it. It's parents.
yeah, but the same could be
That's
for-
none of this is right.
I don't know what their gas man.
That's
I mean,
So no,
Easily measure it.
Never mind.
yeah, until it's measured, it could be.
I gave them 4 sheets of paper.
If there are one or two
And each
different-
sheet
If there was only
double-sided.
one place for it to be at
And they made a copy so that this
Until
is
it's
the
measured,
front,
it could be another one.
this is the back, This is the front. And this is the back.
I'm like, so,
So they made it in, they
It's
took
not
my
actually
4-page packet, and made it
Until it's
into
measured.
2-page packet.
but then you said we
76
want
of them.
to-
It's nice for them.
You
it's
don't
hard
know
for us.
if either one of those two
I mean,
places, so-
What's
They didn't copy
It
the
could be a
answer
super-
for
It could be a
those.
superposition of both places.
Alright, so this is in a very, very, very simplistic way what I'm talking about here. If you had this, okay, so the gas can't be anywhere in between, right? It can either be in this side or this side, so the left side or the right side. So if I just had one gas molecule, what are the two possibilities? It could either be in the left or the right. That's it. So what is the probability that the left side is empty?
50%.
50%. So 50% of the time, there's only two possible arrangements. 50% of the time, the left side would be empty. What if I increase it now to 2 gas molecules? What is the probability that the left side would be empty? 25%. What's the probability that there would be one in each side?
50%.
50%. So does that mean that all of the time it's always going to be evenly dispersed?
No.
But it is most likely in this arrangement, because this has a higher probability than for the left side to be empty. There's a higher probability that there's at least one in the left side than for it to be empty. Now what if all of a sudden I have 8? I know, just 4. I lied, just 4. 4 particles. What now is the probability that the left side is completely empty?
Less than before.
1/16. 1/16. What's the probability that they're evenly distributed?
4. Less than before. No, it's 4.
45.
No,
No,
it's 6/16, which is greater than any of the other possibilities. So what are you supposed to be saying about this? Why is it that when you put gas particles into a container, they're usually pretty evenly distributed? Because why?
Higher chance of.
There's a higher chance of finding them evenly distributed than finding them in any other possible arrangement. That's all. I had to describe it. Okay, so it's kind of what I was just saying. Gases are going to completely fill their chamber because there's many more ways to actually fill it than to be found in one region or another. What does S mean? Entropy. The entropy of a solid is less than the entropy of a liquid, which is much, much less than the entropy of a gas. And why is that?
It's like.
Because what are we really looking at here? Different numbers of positions available. So many more ways for molecules to be arranged as a liquid than a solid, and then many, many, many more ways to be arranged as a gas than a solid or a liquid.
Are we weighing the question again?
You guys are. So I think the next one is the one where I'm gonna see. Yep, it's the next slide where I get to see if you can answer this question.
Is it like a past knowledge question?
Yeah, it's like a whole bunch of past knowledge question stuff put together.
My memory sucks.
Okay, ready for me to ask the question?
No.
Kyle.
Yes.
Can I go on now?
Yes.
Okay. So I'm gonna put it that, so if you still need to write. All right, this is my question. If I put a big beaker up here of water, and I put 1 sugar cube in it, initially it would just do what? Initially it would just sink to the bottom. And then if I covered it up so the water isn't gonna evaporate, so the water is gonna stay in there, and I left it, and we left it like all week and we came back on Monday, what would it look like? Would you still be able to see the sugar cube at the bottom? No, because it would do what?
Dissolve.
It would dissolve. Why would it dissolve? Now this
Ooh,
is
because the entropy of.
okay, so we'll talk about entropy in a second, and I want you to relate it to entropy in a second. But based on what you've known before, and everything we've talked about before, if you had to explain to me, why is it all dissolved when you come in and you look at it? I'm not going to shake it up. I'm not going to crush up the sugar cube. I'm not going to stir it. I'm just going to leave it. Why is it all going to be dissolved and I won't be able to see the sugar in there on Monday?
It's the gas inside the container.
What about it's like all water in a sugar cube?
Okay. So
The water.
the sugar cube will begin to dissolve,
It does, and the water is constantly doing what?
Moving around.